Imagine light coming from stars that died before Earth even existed, racing towards you at a speed exceeding 1 billion kilometers per hour. You think you can estimate its size, but everything you know about scale will most likely be wrong. Beyond neutron stars spinning faster than mixer blades, through cosmic filaments stretching 1 billion light years, and toward regions where space itself was created faster than light, we are about to embark on a journey. If you're ready for your mind to be confused by the true scale of existence, hit the like button, because what's coming next will change how you see everything. You think the Earth is massive because it takes hours to travel from one end to the other. You think the ground beneath your feet is solid and permanent. But here is the truth that will shatter all your beliefs about scale. The Earth looks enormous to us because we experience it step by step. Walking from your home to the grocery store feels like a journey. Crossing your state from end to end takes hours. Flying to another continent takes an entire day. We build our entire understanding of size based on these human scale references. But compared to what truly exists out there, the Earth is smaller than a speck of dust floating inside a cathedral. If you could shrink everything that exists, the Earth would become invisible to the naked eye before you even left your own neighborhood in space. The Moon, which looks small enough to cover with your thumb, is actually 384,000 kilometers away. That's like lining up 10 Earths end to end, and yet you still can't reach our closest neighbor. Your brain may not be able to grasp what this really means. Evolution did not equip us to understand distances measured in millions or billions. When someone says a billion, your brain automatically treats it the same way as a million. But the difference is astonishing. 1 million seconds equals 11.5 days. 1 billion seconds equals 32 years. If the Earth were a marble, our entire solar system would still be smaller than a single city block. And our solar system itself is just one point in a galaxy containing 400 billion stars. You will travel beyond everything your mind can comfortably contain. You will discover objects so dense that a teaspoon of their material would weigh as much as Mount Everest. You will witness collisions that produce more energy in 1 second than our sun will generate in 1 million years. You will encounter structures so vast that light takes longer to cross them than the entire duration of human existence. The big things in your everyday life will become completely meaningless compared to what truly exists out there. The Earth's atmosphere is trying to crush you with the weight of an elephant. Every square centimeter of your body is currently experiencing about 1 kilogram of air pressure. But this gas blanket that keeps you alive extends only a few tens of kilometers above your head. Space officially begins 100 kilometers above sea level. If you could stack average-sized humans on top of one another, you would need 59,520 people to build a tower reaching the edge of space. Most commercial airplanes cruise at only 10 to 11 kilometers in altitude. Even at that height, without pressurization, you would die within 15 seconds. And yet, you would still be only 1/10 of the way to space. Mount Everest rises just 8.8 kilometers. To reach space, you would need to stack 11 Everests on top of each other. If the Earth were shrunk to the size of a basketball, its atmosphere would be thinner than a sheet of paper wrapped around it. Every breath you have ever taken, every cloud you have seen, every bird that has ever flown, exists within this incredibly thin shell surrounding our planet. The International Space Station orbits 400 kilometers above Earth. The astronauts up there aren't floating because there is no gravity. They are falling around the Earth at 28,000 kilometers per hour. The space station, which seems impossibly far away, actually orbits closer to Earth's surface than the distance between New York and Washington, D.C. If you could drive straight up at highway speed, you would reach it in less than 3 hours. And yet, this tiny step represents humanity's greatest achievement in space travel. In all of human history, only about 600 people have traveled that far. Light from the sun hits your face 8 minutes and 20 seconds after leaving the surface of our star. In those 8 minutes, light travels 150 million kilometers through empty space. But here's the part that will melt your brain. In that same amount of time, light could circle Earth's equator 7 times. Our star is so massive that even light, the fastest thing in the universe, needs more than 4.5 seconds to cross from one side to the other. The sun could swallow more than 1 million Earths and still have room left. The sun contains 99.86% of all the mass in our solar system. Everything else combined makes up just 0.14%. If the solar system were a giant pizza, the sun would be almost everything, with only a few tiny crumbs scattered around the edges. The sun's surface temperature reaches 5,500 degrees. That's hot enough to vaporize any material known to exist on Earth. The sun's core burns at 15 million degrees. Every second, the sun converts 4 million tons of matter directly into pure energy. This process has been happening for 4.6 billion years, and it will continue for another 5 billion years. Yet despite this incredible power output, the sun is actually quite average. Astronomers classify it as a yellow dwarf star. Even within our own galaxy, there are stars that make our sun look like a birthday candle. Some stars burn so intensely that instead of a 10 billion year lifespan, they consume themselves in just a few million years. The sun is so far away that it appears as only a small disk in our sky. And yet, if you look at it directly, it is bright enough to permanently blind you. This average-sized star, sitting 150 million kilometers away, completely dominates our planet's energy budget. Without the sun's light, Earth would become a frozen rock with surface temperatures hundreds of degrees below zero. Pluto sits in endless darkness at the frozen edge of everything you call home. This distant world marks what most people imagine to be the edge of the solar system. But Pluto isn't even close to the real edge. Pluto orbits the sun at an average distance of 5.9 billion kilometers. Light from the sun takes more than 5 hours to reach it. Temperatures there never rise above -225 degrees. Pluto represents only the inner boundary of our solar system's true edge. Beyond it lies the Kuiper Belt, and even farther out, the Oort cloud. The Oort cloud extends 50,000 times farther from the sun than Earth does. If you could shrink our entire solar system to the size of a grain of sand, the nearest star would still be 1.5 kilometers away. Our fastest spacecraft, Voyager 1, was launched in 1977 and is still moving away from the sun at 61,000 kilometers per hour. After 47 years of uninterrupted flight, it has only barely left our solar system. It will not come close to another star for 40,000 years. Even at the speed of light, reaching our nearest stellar neighbor would take 4 years and 4 months. Interstellar space contains almost nothing. In the emptiest regions between star systems, you might find 1 hydrogen atom per cubic meter. Earth's atmosphere contains trillions upon trillions of atoms in the same volume. This emptiness stretches in every direction across distances that would take lifetimes to cross, even at the speed of light. Our galaxy is currently eating other galaxies. The Milky Way slowly devours smaller galaxy groups, stretching them into streams of stars wrapped around us like cosmic spaghetti. This process has been happening for billions of years. The Milky Way contains between 200 and 400 billion stars. Each one is a sun, potentially hosting its own family of planets. If you could count one star per second, it would take more than 12,000 years to count them all. But the truly mind-blowing part is the distance between them. Our galaxy measures 100,000 light-years from edge to edge. Light takes 100,000 years to cross from one side to the other. Voyager 1 would need more than 1.7 billion years to make the same journey. By then, the Sun would have burned out, Earth would be gone, and the galaxy itself would have completely reshaped. Our entire solar system orbits the galactic center at a speed of 828,000 kilometers per hour. Even at this incredible speed, completing a single orbit still takes 230 million years. Dinosaurs lived and died during just the last quarter of our orbit. At the center of our galaxy lies a supermassive black hole called Sagittarius A star. This monster contains 4 million solar masses compressed into a region smaller than Mercury's orbit. Stars near the galactic center orbit this black hole so fast that they complete a full orbit in just 16 years. These stars experience such extreme gravity that time itself flows more slowly for them compared to us. A star called UY Scuti is so large that if you placed it where our Sun is, it would swallow Mercury, Venus, Earth, and Mars, and extend beyond the orbit of Jupiter. It would take 9 hours for light to travel around the circumference of this monster. If you could drive around its equator at highway speed, the journey would take 9 million years. UY Scuti belongs to the class of red supergiants. It represents the final stage in the lives of the most massive stars. When a star contains more than 25 times the mass of our Sun, it consumes its nuclear fuel at an incredible rate. While our Sun will burn steadily for 10 billion years, UY Scuti will exist for only about 10 million years in total. Despite being 1.7 billion times larger in volume than our Sun, it contains only about 30 times more mass. That means the star is incredibly sparse. Its outer atmosphere is so thin that it is essentially a vacuum. But UY Scuti isn't even close to the most massive stars we know. Stars in the R136 cluster contain up to 300 times the mass of our Sun, compressed into much smaller volumes. They burn so hot and bright that they hurl their outer layers into space, with stellar winds moving thousands of kilometers per second. When UY Scuti eventually dies, it will likely explode as a supernova, visible from Earth in broad daylight. Despite being thousands of light-years away, the explosion will outshine our entire galaxy for several weeks. A neutron star called PSR J17482446e spins 716 times per second. In the time it takes you to blink once, this stellar corpse completes more than 200 full rotations. Its equator moves at nearly 160 million kilometers per hour. Any faster, and centrifugal forces would tear the star apart. Neutron stars represent what happens when the core of a massive star collapses under its own gravity. In less than 1 second, a region the size of Earth is crushed into a sphere just 19 kilometers wide. The collapse is so violent that protons and electrons are forced together, forming neutrons. A neutron star contains more mass than our Sun, compressed into a volume smaller than Manhattan. The gravity at its surface is 200 billion times stronger than Earth's gravity. A single teaspoon of neutron star material would weigh 6 billion tons on Earth, more than all the cars, trucks, and buses on this planet combined. The magnetic field around a neutron star is 1 trillion times stronger than Earth's magnetic field. Some neutron stars are even more extreme. Magnetars have magnetic fields 1,000 times stronger than normal neutron stars. These fields are so intense that they would wipe every credit card on Earth from a distance of 160,000 kilometers. When two neutron stars spiral toward each other, they create kilonova explosions that forge gold, platinum, and uranium. Every gold ring, every platinum catalyst, every uranium atom on Earth was created inside these cosmic collisions billions of years ago. On August 17, 2017, gravitational wave detectors felt space itself vibrate. Two neutron stars collided 130 million light-years away. The merger, known as GW170817, lasted just 100 seconds, but released more energy than our Sun will produce in its entire 10 billion-year lifetime. Even though the collision occurred in another galaxy, it created an explosion called a kilonova that was visible to amateur astronomers. When two neutron stars merge, they create conditions found nowhere else in the universe. Temperatures reach 100 billion degrees. The collision hurled pure heavy elements equal to about 50 Earth masses into space at thousands of kilometers per second. Dark matter outweighs all the stars, planets, gas, and dust in the universe by a ratio of 5-to-1. Every atom in your body, every grain of sand on Earth, every star in the night sky represents only 16% of all existing matter. The remaining 84% is completely invisible and interacts with normal matter only through gravity. We know dark matter exists because we can see its gravitational effects on everything. Galaxies spin too fast to hold themselves together using visible matter alone. Right now, billions of dark matter particles are flowing through your body without interacting with a single atom. Despite decades of searching with increasingly sensitive instruments, scientists have still not directly detected a single dark matter particle. The leading theory suggests that dark matter is made of particles created in the first moments after the Big Bang, but with properties completely different from normal matter. The Milky Way is trapped inside a spherical prison of dark matter that extends 3 times farther than the visible edge of our galaxy. This invisible halo contains 10 times more mass than all the stars, gas, and dust we can observe. Without this dark matter cage, our galaxy would have fallen apart billions of years ago. Dark energy is tearing the universe apart at an accelerating rate. This mysterious force makes up 68% of everything that exists, and yet we have no idea what it actually is. Dark energy behaves like anti-gravity, causing space itself to expand faster and faster. 5 billion years ago, dark energy overcame gravity and began accelerating the expansion of the universe. Now, dark energy dominates, and the rate of expansion increases every day. The universe will expand forever, becoming colder and emptier with each passing billion years. On small scales, dark energy has no effect at all, but on the largest scales, dark energy rules everything. In the distant future, dark energy will create a lonely universe. Every gravitationally bound group of galaxies will be isolated inside its own bubble of expanding space. Stars will fade, black holes will evaporate, and the universe will drift toward maximum entropy. A supermassive black hole called 3C273 shines with the light of 1,000 Milky Way galaxies. Smaller than our entire solar system, this monster sits at the heart of a distant galaxy, devouring stars and gas at such a furious rate that it outshines every object in its cosmic neighborhood. The energy it releases in 1 second equals what our Sun produces in 10 million years. Quasars represent supermassive black holes in their most violent feeding stages. When galaxies collide or merge, huge amounts of gas are funneled into the central black hole. This material forms a superheated accretion disk that shines brighter than anything else in the universe. The brightest quasar we have discovered shines with the luminosity of 40 trillion suns. This single object, fed by a black hole 20 billion times the mass of our Sun, releases more energy in 1 second than would be produced by merging 400 billion stars. It is so bright that we can see it from more than 12 billion light-years away. Quasars also launch material jets at 99.9% the speed of light. These jets extend millions of light-years beyond their host galaxies. The closest known quasar is 3.2 billion light-years away from Earth. Even at the speed of light, the journey would take 3.2 billion years. The farthest quasar, J0313-1806, existed when the universe was only 670 million years old. Its light has been traveling toward us for more than 13 billion years. Cosmic expansion has carried that quasar to a distance of more than 46 billion light-years from us today. At such vast distances, we are not only looking into space, we are looking into the distant past. When we study the farthest objects, astronomy becomes archaeology. As quasar light travels across cosmic distances, it passes through gas and dust clouds that leave absorption fingerprints in its spectrum. These absorption lines map the distribution of matter across the universe like a cosmic barcode. The vacuum of space contains dark energy that outweighs every star, planet, gas cloud, and black hole in the observable universe by more than a factor of 2. This invisible energy fills every cubic centimeter of empty space. Dark energy makes up 68% of the universe's total mass energy content. Dark energy behaves like a cosmological constant, providing a repulsive force that opposes gravity on large scales. The acceleration caused by dark energy began to dominate cosmic evolution about 5 billion years ago. The local group of galaxies spans 10 million light-years and contains over 80 individual galaxies, yet it occupies less than 1% of the volume of a typical cosmic void. Cosmic voids represent the largest structures in the universe. The largest known void, the Boötes void, is 330 million light-years wide and contains almost no galaxies. The boundaries of voids are defined by galaxy sheets and filaments that form the cosmic web. These structures contain most of the ordinary matter in the universe, organized into networks spanning hundreds of millions of light-years. Galaxy clusters form where multiple filaments intersect. Cosmic filaments stretch for hundreds of millions of light-years, forming the largest structural elements in the universe. These dark matter and gas strands connect galaxy clusters like a vast three-dimensional web. The filament containing our local group extends for over 500 million light-years. Individual filaments can contain the mass equivalent of 10 trillion suns stretched along their length. Despite their enormous size, filaments are surprisingly thin, typically only a few million light-years wide. This creates structures with aspect ratios more extreme than a human hair compared to its length. The Hercules Corona Borealis Great Wall stretches 10 billion light-years across space, making it the largest structure known in the universe. This cosmic wall contains billions of galaxies, and light would take 10 billion years to cross from one end to the other. The Great Wall is so massive that it challenges our understanding of cosmic structure formation. Theoretical models predict that structures this large should not exist because gravity has not had enough time since the Big Bang to pull them together. If the universe is finite and curved back on itself, we may be observing the same cosmic objects multiple times without realizing it. Light from a single galaxy could travel around the curvature of the universe and reach us from different directions, creating duplicate images separated by billions of years. The cosmic microwave background represents the farthest edge of the observable universe. It is the glowing shell of ancient light, marking the moment when atoms first formed and the universe became transparent. This radiation has been traveling toward us for 13.8 billion years, carrying information from when the universe was only 380,000 years old. The tiny temperature variations in this radiation, only a few millionths of a degree, represent the seeds that would eventually grow into galaxies, stars, and planets. Every structure we see today began as microscopic fluctuations in this ancient light. This ancient radiation fills the entire universe uniformly. Every cubic centimeter of empty space contains about 400 cosmic microwave background photons left over from the Big Bang. These photons have been redshifted by cosmic expansion from visible light to microwave frequencies. The observable universe is only a small bubble inside a cosmos that potentially extends infinitely in all directions. We can only see light that has had time to reach us since the Big Bang, creating a spherical boundary 46 billion light-years away. Cosmic inflation theory suggests that the entire universe is far larger than the part we can observe. In a fraction of a second after the Big Bang, space expanded exponentially. Conservative estimates suggest the entire universe is at least 10 to the 23rd times larger than the observable portion. An infinite universe would contain infinite copies of everything, including you, Earth, and exact duplicates of our entire observable region. The laws of probability guarantee that every possible arrangement of matter will occur infinitely many times across infinite space. Cosmic inflation expanded a region smaller than a proton into something larger than a grapefruit just 10 to the negative 35 seconds after the Big Bang. This exponential expansion increased the size of the universe by at least a factor of 10 to the 26th, turning quantum-scale fluctuations into the seeds of galaxies. If inflation is correct, there is a striking answer to the question, how big is the universe? It is either impossibly larger than what we can observe, or literally infinite. The universe started smaller than the period at the end of this sentence, then grew to be far larger than anything you can imagine. The words you are reading right now, this screen, this planet, were once a point so small it couldn't be seen. Then, in an instant explosion, space itself expanded and over billions of years evolved into the cosmic scenery we see today. Every atom in your body was forged in the heart of a star. The oxygen you breathe, the calcium in your bones, the iron in your blood were all created inside stars that died billions of years ago. You are literally stardust. And here is the most striking truth. Despite all this incredible scale, all these cosmic time frames, all these unimaginable distances, we are still here, now, living this moment. We exist as an island of consciousness in an ocean of infinity. Does your sense of scale mean something different now? We can discuss it in the comments. Good night.